my name is Brevin Higman. You can call me Hig. I'm a geologist. I've got a doctorate in geology from the University of Washington, Seattle. I've worked on geologic hazards, and particularly on the geologic records of these. And so these are kind of problems where you're trying to figure out what sort of evidence is there for things like tsunamis, earthquakes, volcanoes, big events that have happened in the distant past, perhaps, and how would you detect those in a given spot. And I really enjoyed all the presentations today. It was really neat to see the kind of back and forth nature of this. Unfortunately, the seismic, the other half, I guess, I'm an independent consultant, not working for Pebble. The other half of that isn't here, and I think that in some ways my presentation will contrast a lot with some of the presentations you've seen. One way is that actually I'm not going to present any of my own work. I have worked on this. I've been at the Pebble site a number of times. I've done field work on seismic hazards for 3 field seasons in the general area around Pebble. But I will not be presenting on that today. I'm happy to answer questions about it, but my focus is going to be on the material that is in the environmental baseline document, the EBD. So here's the title I chose. This is a nice punchy title, but really what we want to know is, will there be earthquakes at Pebble, right? It's not, are there earthquakes at Pebble? And this is because there's going to be facilities at Pebble, and some of these facilities may be vulnerable to shaking from earthquakes, to other effects of earthquakes. And in particular, the large tailings dams that are likely to be needed for any future mine. And so what we'd really like to know is, once things are built, could there be a big earthquake right there that might damage these facilities? However, this is actually a very, very difficult question to answer. There are a few ways you can approach it, but it's difficult to directly measure the stress in the earth and this sort of thing that might lead to an earthquake. So what we typically actually try to figure out as geologists is, have there been particularly large earthquakes at a given site, in this case Pebble, in the past? And so that's really going to be the main focus of what I'm talking about. I'll touch a little bit on other things, but mostly what I'm talking about is looking into the past, and can we, what would we do to figure out if there have been earthquakes? If the past is very recent, then it's fairly easy. This is Peter Heusler from the USGS. He's looking into a fissure that was opened up on the Susitna Glacier during the 2002 earthquake on the Denali Fault. It's very dramatic effect, but of course a glacier is moving and transient, and even if you went there now, you wouldn't be able to see this feature. The map below just shows a little section of that earthquake rupture. The black parts of that line are places where the ground was broken by the earthquake, and the blue are places where glaciers were broken, like this. And one thing I just want to draw your eye to is this little band of rifts and fissures in the ground over here. First of all, very complex, and also not along the main path of the fault that was the Denali Fault. This was the Susitna Glacier Fault, which was previous to this earthquake that it was not even known to exist, which was one interesting aspect of this recent earthquake. So if you go to the Pebble site and you look around, you don't see any big crack in the ground. Does that mean we're done? There are no obvious earthquakes have happened here. But so of course, it's a very difficult thing to figure out if you're looking into the distant past. Like, has there been an earthquake in the last 100 years? Last 100 years we have instrumental records, but the last 1,000 years, the last 10,000 years, it's a very difficult question to answer. We can look, for example, down to Washington, where there's a lot more money for this kind of research. People have done a lot of research, and they look at one data set that's commonly looked at as LIDAR. It's basically elevation data. To orient you, here's Seattle and another community called Bremerton, which I'm going to focus in on here. And we'll look at what the topography looks like right here in detail. And there's a lot of things going on here. This is a very, very high-resolution data set. You've seen some examples of this up at Pebble. You can see gullies, you can see roads. There's a beautiful road right there. It picks that out very nicely. And the thing that paleoseismologists, people looking for evidence of old faults, are looking for are these here. These funny lines that, it turns out, do a lot of looking, and there aren't any other explanation for them. People have gone and dug trenches across these, and these are active faults. Now notice they're not that big. This is only this is about a mile long here and here. These are features that, on the scale of thousands of square miles, they're a pretty subtle feature. You got to really look for these to find them. So yeah, these are named faults now. I was really excited to hear about the EBD being released, and part of this was because I had a conversation with Ken over email a year ago, And he described what was going to be released in this document. He says that there was an analysis going on by experts in the topic of seismology, and they were analyzing all these great data sets that Pebble had. And most interesting to me was this aeromagnetic surveys, but there was other data being analyzed as well. And so I was very excited to open the EBD up and see, because there's so little known in this area about earthquake hazards. And first thing that surprised me is there is 4 pages out of this 30,800 that cover seismic hazards, plus 3 figures. But so if you're really going to count out everything, 7 pages. There's no mention of this aeromagnetic data that I was excited about. There's actually no analysis of Pebble's data at all, and no original research. They do reference one Pebble study, but it was not a study about seismic hazards. So you might think, okay, well, they didn't do much, and this would be like some of the sections where there's future studies perhaps, and they just kind of have a placeholder to say, well, we don't know what's going on. But actually, they draw a very strong conclusion at the end of this analysis. And they basically say there is no seismic hazard, that we don't need to worry about earthquakes at Pebble. And this is very surprising to me, and I want you to keep this conclusion in mind, because a lot of what I'm going to look at here, if these were idle speculations, they would be fine science. The sort of conversation you might have over the dinner table, like, well, maybe there's a fault over here, or maybe there's not, or whatever. That's great, and there's a lot of that in here. But the fact that they then took those, what are my idle speculations, and drew a conclusion that they would then use to inform a mine plan is very worrisome. So, give you a general bit of geography here. This isn't the most recent mine claim map. I'm using the one that Pebble used in that section. But these are the big faults that are in the general area. Of course, the one that probably is jumping out at you right away is the Lake Clark Fault. And so this is a major fault that's been mapped for some distance. And the reason it seems like it might be one worth looking at is that it is headed straight towards Pebble when mapping ends. And this is not, there's no indication this is the end of the map, the end of the fault there at the southwestern end. And in fact, we know it's not the end of the fault, because the fault is shifted by 16 miles at that point. It can't just abruptly stop there. And so you think, well, gee, that might go very close, may even go through the Pebble prospect. And so what does Pebble say about this? Well, the first thing they say is that the Lake Clark Fault is considered inactive by the USGS. And if this fault was inactive, meaning if it was incapable of producing dangerous earthquakes, well, then it wouldn't matter if it went right through the site. It's just, it's something that produced earthquakes in the distant past. Today it doesn't. It presents no hazard. So let's look at that in a little more detail. They reference a particular USGS publication here, Heusler and Way Thomas, 2011. And this is a report. It doesn't do original analysis other than to look at actually a hole in the ground I dug and talk about what was seen there. It doesn't actually look at the regional geology, but it does provide a summary at the end, and they make this very equivocal statement that, if we did a bunch of work, we didn't find anything, then maybe there's nothing to find. However, the important document they reference is actually a Department of Natural Resources report that does do original work. And here they make it very clear. They say the paleoseismic history of the western part of the Lake Clark Fault is unknown. So this is the real state of the science. We don't know. And that contrasts very sharply with the Pebble EBD's statement that the Lake Clark Fault is considered inactive. And this picture in the back actually shows where some of the most interesting discussion is going on, is on this very subtle feature here up by Beluga, which appears to cut across glacial deposits that are a few 100,000 years old. So another really important part, if you're going to take the tack of trying to, looking at a fault and discounting it because it's inactive, that is actually very, very difficult science. It's something that we get wrong all the time. It's virtually impossible, and not impossible, just almost impossible, to prove that a fault cannot produce large earthquakes. And this example here, this is the 1999 earthquake in California at Lavac Lake. This was a mapped inactive fault, and it ruptured it released a magnitude 7.1 earthquake, broke the ground for 25 miles. Not the sort of thing you want to have happen underneath your house or underneath your tailings facility if you should happen to have one. So what's the next step here? So just to summarize, are we sure the Lake Clark Fault is not active? It's a very clear no. This is not a maybe not sort of thing. We do not know. This is I think we can say without any doubt that we do not know. All right, so the EBD does not actually say that Pebble doesn't think the fault is active. It just says the USGS doesn't think it's active. But how do they square that then? If they think maybe this fault is active, how do they square that with their statement that that the seismic hazard here is not significant? So this is the mapping that they prefer, and they don't quite draw it as boldly as I do here, but it is very, very strongly implied in this section. They think the fault abruptly veers and avoids the mine site, which would be surprising if you look at this map. I mean, that isn't what might jump to mind. You know, you'd need some pretty strong evidence. Sorry, that's printed over each other. You need strong evidence to really show that fault does this. It takes this rather surprising bend one way or the other. So I'm going to look at the two lines of reasoning they use in order to draw this conclusion. So the first one they use is they look at some faults, including the Lake Clark Fault, and they see that on occasion the fault breaks up the rock, glaciers scoop that rock out, and the glacier flows down the fault. So if the glacier follows the fault, maybe then faults follow glaciers. And then they show this map here on the right, and they say, well, look, the glaciers flowed around the upland that the prospect is in, so the fault probably goes around it too. So that's the first reasoning they use. And there might be reasons you would question this on the basis of kind of your understanding of how the world works, but we can just simply go in and look at some examples here. And there are many, many examples where faults cross glacial flow paths. This is right near my home in Soldovia. There's the Denali Fault, got glaciers crossing it all over the place. And even the Lake Clark Fault, actually, just a little further to the northeast, has major glacial flow crossing the fault. So I think that we can, again, you know, it's exciting as a scientist to be able to draw really bold no sort of a conclusion. And I think we can do that here. You know, faults do not actually follow glaciers. They then pull out another really interesting idea, and this is one that you all could see the problem with just from having watched the presentations we've already seen today. And they say that the study area is in these volcanic rocks, these plutonic rocks that are very strong, and that it's likely that faults wouldn't break that. Now, we've been hearing several times today about the faults that do break this very body of rock. And so on this map, all of these lines like this are faults. And actually, most interesting of all is this system of faults here. There's a series of parallel faults that cut. There's the mine, or the deposit right here, and there's this system of faults right here. These are the most prominent faults in the area. You notice that we don't have any body of rock that's mapped right across it, so we don't have a sense of what offset is. Now, if you were to employ what's sometimes called Occam's razor, that the simplest explanation is most likely to be right in the absence of other evidence, we have a great absence of evidence here, so we can do this sort of thing, then you would say, well, the Lake Clark Fault's somewhere up here on the ceiling, coming down this way, and well, look, there's this fault system that's a major fault system that's aligned with that. And in fact, the EBD notes this in chapter 3 where it talks about this. Maybe they're one and the same. Maybe this is the Lake Clark Fault right here. Now, of course, this is a big maybe. I don't know that that's the Lake Clark Fault. I don't have any direct evidence of that. But it is the simplest explanation. And if we were to work with the data we have today, it would be best to assume this. Assume that the fault actually bounds the mine deposit, that there could be potentially very large earthquakes that would occur right in the mine facilities. So, yeah, is the pebble rock too strong for faults? No. And to summarize here, are we sure the Lake Clark Fault isn't active? No. Do faults follow glaciers? No. And is pebble rock too strong for faulting? And that's a definite no as well. Now, let's look around at what other projects are going on, and is anyone in a similar position? I mean, you know, Pebble, they're a resource development company. Should they be expected to go out and look for active faults? You know, it seems rather onerous. And there are actually companies that are doing this. And what I did is I asked around the folks I know who work as consultants doing this kind of work and said, okay, what are the really good projects? What are the projects where you were given the freedom? And the sort of freedom I hear from talking to the Pebble consultants that they had in their studies of fisheries and water quality, the freedom to do good science. Where are these happening? One of them is the Alaska Pipeline Project, which would pipe natural gas from Alaska Lower 48. The scientists have done real original work looking for evidence of active faults there. Another one is this large nuclear power plant in California. So there are actually examples. They actually found a big active fault just offshore of this facility as a result of the science that the nuclear power plant funded. So yeah, we got a yes there. Now there are a couple of things I want to touch on at the end here that are they're sort of different pieces of this puzzle that go outside the sort of looking at evidence of past earthquakes. And one of them is the question of could building the mine itself have the possibility of triggering or inducing earthquakes. And there is actually a process by which this can happen. And if you add a lot of weight to the landscape, or if you change the water table, especially when you raise the water table, these two things can lead to earthquakes. Actually, if you subtract a lot of weight from the landscape, that can also. And so you're basically, if you do something that changes the stress field, it changes the forces on the earth, or that changes the strength of the rock, then an earthquake can happen. And typically, these earthquakes are not very large. They're not as large as a lot of as the sort of earthquakes the whole Lake Clark might produce. That Lake Clark fault could produce like a magnitude 7, 8, maybe even 8, a fairly large earthquake. These you might be looking at a 5 something, you know, and that would be much less of a concern. The only situation that's really important to think about here is if those should trigger a earthquake directly under an important facility where it would actually shift that facility. So it's not just a matter of shaking in that case, it's a matter of cracks opening, say in a tailings dam. Then that would be a larger concern. And this is actually it's a small crack that popped up in the bottom of a quarry in California. It's in that photo. Another interesting area of emerging science is seismic focusing, and so there's an idea that if you have an earthquake, if you go further from the earthquake, of course, the shaking decreases. This is a very confusing figure. It's the best one I could pull out of this paper. But basically, these folks looked at the Haiti earthquake, and they found this area on this ridge where there was higher shaking than was expected. And it was higher by a factor of several. It was over 2 times as strong as would have been expected otherwise. And so this is a factor that I think that Pebble should be working to model in their seismic hazard assessment. And so this is a curve, this is a graph I actually pulled from Pebble's earlier work. It's very slightly different. It's actually higher now in their recent stuff that I've just seen very recently. But it's a curve that looks at the strength of shaking, which is measured in this peak ground acceleration number on the left, as you move away from the fault. So if you are 20 miles away from the fault, the shaking is much less than if you were right on top of it. So that's what this basically says. And there's going to be some sort of design criterion for the facilities, and particularly these tailings dams, that will say we're designing to withstand a certain amount of shaking and not above that. And previously they were talking about 1/3 of a G, 0.3 G. And that would be the green area would be okay, and the red area would not. So of course the location of the fault matters a lot here. If you were out at 20 miles, we're in the green, but if you're at 2 miles, we're way up in the red. And the earthquake would be several times as strong as what the design criterion set. But if you then added in this seismic focusing thing, which the facilities themselves, these tailings dams, if they approach anything that our best guesses say, they might be large enough to be seismic focus to focus seismic energy themselves. Well, then you might be looking at something that's up here. So even if we're talking about more distant earthquakes, it could be a problem. This is another factor that I think should be considered in here, but isn't even touched on. So the bold bullet point summary here. Pebble has not published good earthquake science. And I don't say that lightly. I mean, I actually think a lot of what we heard today is good science, and people have had the and working for Pebble have had a chance to do good work. But in this particular section, the section where I happen to know something about it, which I know very little about fisheries and such, it's really not good. Don't know how to say it any nicer. The conclusion that they draw is not just questionable, it's also very optimistic. So it's a conclusion that suggests that they are attempting, that they have a preconceived notion about this, that they'd rather not think about seismic hazards here, and they're trying to pull that out of their interpretations. Rather than that they just hired a harebrained guy who came up with some wacky ideas and got something wrong, it's wrong in a very specific direction. Every conclusion they draw that seems to deviate from reality points in the same direction, towards underestimating seismic risk. And so that's worrisome. And if they get this wrong, it's a real problem. This is, an academic debate to some extent, but if this seismic hazard is what is going to inform the engineering of the mine tailings facilities, and if that engineering is wrong and there's an earthquake that exceeds what they expect, those dams could fail, which is a terrible, terrible scenario, and one that we really hope there's no chance of if this mine is built. And so that's what I have for you today, and thank you very much.
Thank you, Hig. I don't even think he messed up with this, so you're the next trainer too, Hig, on this. Appreciate that.
I was ready for it, but
Any questions right off the top here for Hig?
I don't know if Ken would like to speak to what's the studies that, because you referenced some studies that were being done when we emailed. I don't know if you caught the beginning of my talk there, but I referenced this email, and you mentioned some studies that were being done, and those didn't appear in the EBD. Are those studies ongoing, or are there conclusions contrary to what I presented here?
Well, thank you. I actually tried to get our seismic expert up here to talk about his work, but he was already booked, and I'm not a seismic expert by a long way. The state of the science in 2009 was that the Lake Clark Fault was undetermined, as DNR published in the DGGS report. In 2010, USGS came out and did some further studies, and in their report, those determinations that you presented were their determinations, not ours. In fact, I believe the report says the Lake Clark Fault hasn't been active for the last 1.8 million years, and a fault is, under USGS definition, determined inactive if there's been no activity for 10,000 years. So that's the definition. Now, whether or not we're concerned about the question, whether Pebble is concerned about seismicity, of course we are. And obviously it's one of the big questions in everybody's mind. And it does warrant further study. Our geology department has been doing studies since 2008 on a number of things that I don't really understand. One of them is called a spectrum survey, another one's called a ZTEM survey. They've been doing induced polarization surveys and more seismic surveys to give us a better idea of the faults in the area. And we do have faults. There are a number of minor faults that you referred to, like the ZG fault that runs through the eastern part of the ore body. But we haven't seen any fault activity. And I think the question is, how long will it be before we see an earthquake out there, and what would the magnitude of that earthquake be? I don't recall ever seeing the graph that you presented with, Pebble considering a 2 to 3 magnitude earthquake as the probable earthquake out there. I'm sure that the people
that's not a 2 to 3 magnitude. That's 2 to 0.2 to 0.3 G's of ground acceleration for a 7.8 magnitude earthquake at some distance from the mine.
Well, it's not just distance from the mine that matters, but it's how deep in the ground as well. So both of those factors have to be taken into consideration. And I think it's going to be a while before anything is built out there, and the studies on seismicity will continue, and we'll have better information in the future.
The USGS report, it does discuss there being no evidence of activity since 1.8 million years ago. That's true, but it does not say that there has been no activity since 1.8 million years ago. There is very little work that's been done, and that's the reason. I mean, it's an easy confusion to have that absence of evidence may appear to be evidence of absence. That if you don't know what's going on, maybe it's all good, but that's all we have at this point. There is really no work that's been done on the sort of active tectonics that's out there. And in order to do that, there are very specific ways you proceed. And actually, aeromagnetic surveys are a useful tool for this. But much better is to be working with extensive LiDAR data sets, which, as far as I can tell, you guys haven't been analyzing at all. They collected a lot. And to be going out and doing geology on the ground. There are approaches that have been used for this sort of study for a long time, and all across California, and they still come up with surprises, and they find faults that just very recently there's a big fault that runs right through a big dam that they thought was inactive. They'd looked at it many times, and a grad student went out and found a place where sometime in the last 10,000 years there'd been major ground movement and obvious evidence of activity, but that had been missed for a long time. And the sort of level of study we have there is far above what we have here. Yes, Craig?
Wasn't there an earthquake out there out in Dalton? It was near the mine site. I mean,
well, there was an earthquake in, I think, 2007. That was a little bit west of the mine site. Significant earthquake for magnitude 4, and then if you look in the catalog of earthquakes, there are several others, including one almost right in the mine site. These are all fairly small earthquakes, but they do tell you that this area it's not tectonically dead. And these earthquakes, one important point is these are not like there's a subducting slab deep below Pebble. But these earthquakes are not way down there, 150 kilometers below the mine site. They're actually in the upper layer of the crust. They're very near to the surface. And this one that was recent, I think 2007. Can you remember the? I think 2009. 2009. Oh, okay. Yeah. Anyway, it was in the top few kilometers of the Earth's crust. So very shallow, and definitely indicating that it's not totally silent anyway in this thing. Yep.
One of your comments had to do with the likelihood of an earthquake might be increased if there were removal of material or other kinds of disturbance at the surface. And I was wondering, is there any evidence of that? Because if there is, creating an open pit mine, maybe the largest one in the hemisphere, with multiple explosions 3 times a day might actually cause some disturbance at the other surface.
Sure.
Before Hig answers that question, we'll have him conclude with this one, and then we'll round robin on our questions. Go ahead, Hig.
So the places where you worry about this sort of thing, this induced or triggered seismicity, is where the things that people are doing line up with the geologic forces. So if the Earth and people are pushing in the same direction, that's when you tend to have earthquakes. So the example I gave you with the photo that showed the quarry, that was a place where things were pushing together and they wanted to pop up like this. And so when they removed a bunch of mass, that enabled that, and it popped up. Now at Pebble, we actually have a different situation, and the mine site is right next to this big graben, which is a place that actually wants to go down. So digging the pit probably would, at least from what we know, would not trigger earthquakes. However, you've got the other thing going on too, which is to build these huge tailings facilities. And if one of those tailings facilities were to be built over, especially it's like Frying Pan and the upper South Fork Cockatoolie, then it would have this nature of pushing in the same direction as the Earth and potentially triggering an earthquake or inducing one. You also have the effect, now, and this again, the mine site, the mine pit itself would not have this effect because they're going to draw water table down. But when they build the tailings facilities, they're going to raise water table possibly by 700-800 feet. And so in doing that, they increase the water pressure in the ground, and that makes it easier for faults to break. So stress that may have been sitting in the earth for a long time, when you raise the water pressure by building these tailings facilities, that could possibly trigger earthquakes. But this is a very shallow level analysis. This is something that it would be great to have a bunch of geologists spend a bunch of time modeling. I'm giving you the broad brush look here.
Let's thank Brentwood and Hickman, please. Thank you. I think we have the opportunity to do a little bit of question and answer now for the next half an hour. And we have a few cards here that have been written by you all. And I think